Hello and welcome to educator.com. Today is our first lecture, and to start with molecular biology, first we have to do a little bit of biochemistry review, and we're specifically going to focus on the importance of the chemical bonds. So as our overview, first we're going to talk about chemical bonds. We're going to talk about both covalent and non-covalent bonds and the different types of each of those. We'll follow that up with the properties of water, as well as chemical reactions and free energy. And then we'll have just a brief intro into the properties of DNA before we finish and move on to lecture 2. So, chemical bonds are attractive forces that hold atoms together, thereby making molecules. So, at least 2 atoms together. Our types of chemical bonds are covalent, which are much stronger bonds. They can be either polar or nonpolar. And then our other class of bonds are the non-covalent bonds, which are much weaker than the covalent bonds. However, when you have many non-covalent bonds together, they can become very strong. The many types of non-covalent bonds, the ones we're going to talk about: ionic bonds, hydrogen bonds, hydrophobic interactions, and finally, van der Waals forces, or van der Waals interactions. So, let's start off with covalent bonds. They are very strong. They involve the sharing of an electron pair between 2 atoms. And making and breaking covalent bonds usually requires the presence of an enzyme to catalyze that reaction. Okay? And the valence number of an atom determines the number of covalent bonds it can form. So what does that mean? First of all, what is the valence number? That is just the number of unshared electrons in an atom's outer shell. So, the common atoms that we are going to see in molecular biology are hydrogen, oxygen, nitrogen, carbon, phosphorus, and sulfur. Okay? So how many valence electrons do each of these have? So hydrogen has 1 valence electron. Oxygen has 6, nitrogen has 5, carbon 4, phosphorus 5, and sulfur 6. So, I said that the valence number of an atom determines the number of covalent bonds it can form. Well, how is that true? Let's show you. So the key here is that all atoms, other than hydrogen, want to have a full octet, meaning a full 8 electrons in their outermost shell. Okay? So, that will determine how many bonds it can make. Okay? So, hydrogen, I said, was the only one that doesn't want 8. Okay? And that is because hydrogen, its full electron shell consists of 2 electrons. Okay? So, every bond is a sharing of a pair of electrons. Okay? So, with hydrogen having a valence electron, 1 valence electron, and it only liking to have 2, okay, to fulfill it, it can make one bond. Okay. Oxygen, to have its full octet, can either accept 2 electrons from somewhere else or give up 6 of its own, but it's more likely to take 2. So therefore, by taking 2 electrons, each one of those is going to participate in a bond. So that is 2 bonds for oxygen. Nitrogen, to get its full octet, would want 3 bonds. Okay, sometimes it can actually have 4 bonds. Carbon, to get its full octet, wants another 4 electrons, so 4 bonds. Phosphorus actually is kind of a little different in the fact that it will more likely give up its 5 than take on 3, so it'll have 5 bonds. And sulfur is a little bit weird in the fact that it's a little more variety. It will make a possible 2, 4, or 6 bonds. Okay. Now, the number and types of bonds ultimately determines the geometry of what the molecule will look like. So, single covalent bonds, so that would be like, say, this, for example, a nitrogen. That would be a single covalent bond, which is a sharing of 2 electrons. Allow rotation of the atoms around the bond, meaning this can flip upside down, right? Flip, okay, maybe even curl a little bit. Double and triple bonds, so for example, a double bond, that's a sharing of 4 electrons, or a triple bond, the sharing of 6 electrons between there. Don't allow any rotation around that bond. So bond angles are actually determined by the number of atoms, and the whole goal is to space out the electrons because the electrons are negatively charged. If you've ever played with magnets, you know that 2 things of like charge want to push away. They repel, right? 2 negatives or 2 positives repel. A negative and a positive attract. So chemical bonds can be broken down into your polar and your nonpolar bonds. Now, your polar bonds, also called electric dipoles, this is a bond between 2 non-metal atoms with differing electronegativities. Okay, and what that basically means is that they are not sharing the bonding they're not sharing the electrons equally. Okay, so let's say for an example, one of the examples is hydrogen chloride. Okay, yes, they have just a bond right there, but what we actually find is that the chlorine atom actually has a partial negative charge, whereas the hydrogen atom has a partial positive charge because the electrons are being pulled by chlorine because it has a higher electronegativity. And if you look at the periodic table, electronegativity decreases as you go downward and as you go leftward. Okay, so you decrease electronegativity as you go down and to the left. Okay. A nonpolar bond, on the other hand, is a bond between 2 metal atoms with similar or even equal electronegativity. So an example of that would be, let's go back to our nitrogen. Right? So that would be an example of a nonpolar bond because nitrogen, if we find nitrogen, right? If you have a nitrogen with an electronegativity of 3.04 and another nitrogen with an electronegativity of 3.04, they're exactly the same, so electrons are evenly shared. Whereas this chloride, right, this is a 3.16 electronegativity. Hydrogen over here is a 2.20, okay? So electrons will move toward the chloride. Okay, good. So now some examples of our non-covalent bonds, or what a non-covalent bond is, right? So they are not the same as the covalent bonds, right? So they don't have that real nice sharing of the actual electrons, right? These are not electron sharing. So ionic bonds, hydrogen bonds, hydrophobic interactions, and van der Waals forces are all examples of non-covalent bonds. Okay? Ionic bonds being the strongest, van der Waals forces being the weakest. So, ionic bonds form between charged groups, otherwise known as ions, and they are the strongest of the non-covalent interactions. So an example, let's say, our sodium ion, our chloride ion coming together to make sodium chloride, otherwise known as table salt. Hydrogen bonds are a type of dipole-dipole interaction between a hydrogen atom and a highly electronegative atom, usually being your oxygen, nitrogen, sulfur, or fluorine. Okay, as I mentioned before in an example of a polar bond, I used hydrogen and chlorine, right? Hydrogen chloride as being a polar bond. But hydrogen and oxygen, okay, or hydrogen and nitrogen, right? Those are not polar bonds. Those are examples of hydrogen bonds, okay? Now we have non-covalent bonds, the other two left, all right? We have hydrophobic interactions, and those occur between non-polar molecules to limit their interaction with water. Think of droplets of oil in water and how they come together to form a bigger droplet. Okay, and I'll explain that a little bit. And finally, van der Waals forces. Okay, these occur between all molecules as a result of unequal distribution of electrons. Okay, so these can be either attractive or repulsive. Okay, and all together, when we're talking about these bonds, multiple weak bonds can have an additive effect to stabilize molecules. And we'll see that throughout this course, especially for DNA. Hydrogen bonds not very strong, right? Van der Waals forces not very strong. Hydrophobic not very strong. But those together actually hold our DNA. They hold the two strands of DNA together, right? So a lot of very weak bonds added up over the length of a molecule can be very strong. Okay. So let's get some examples of covalent and non-covalent bonds. So covalent, we'll do in blue. All right, we'll say polar. An example of a polar one, right? So unequal distribution of electrons. We said before HCl. And I'll give you another one. CH4. Okay, so what CH4 looks like this. Okay, and there's equal sharing between the carbon and hydrogen in all of those. Okay, non-polar. We have, let's say, the one that we talked about before, N2. We have O2. You know, any diatomic molecule, right? You put them all together. Hydrogen gas, right? Sulfide gas. Or even the carbon bond in an ethane molecule. So this is what ethane looks like. Okay, or we could even draw that out to look like this. So all of the carbon-hydrogen bonds are actually covalent, in polar covalent, but the bond between the carbon and the carbon is actually a non-polar covalent bond. Okay, so the non-polar, let's put in green, this is actually non-polar. Okay. Now, let's give some examples of, oh no, what else do we have? Some examples of our non-covalent. So let's say ionic. I gave you one already. Sodium chloride. And that's going to be the strongest, right? We have hydrogen bonds. Those are going to be like the ones that are shown for water, right? And they're usually longer than covalent bonds. And let's see right here if I can draw one out. And by the way, water, those are covalent bonds, okay, between the hydrogen and oxygen. And it would be a polar covalent bond. So I'll even draw that one up here. Okay. H2O. Okay. Okay, so these are polar bonds, right? Or covalent bonds, polar. And then if I draw another water, this right here, the bond between the oxygen and the hydrogen of two separate molecules is a hydrogen bond. Okay. Now we have hydrophobic interactions. Hydrophobic interactions, that would be like water and oil droplets. And then van der Waals. That's just say when any two molecules come together, okay, there is a point at which they are attracted. Okay, and that point is 4 to 10 angstroms. Okay, so there's an attraction between 4 and 10 angstroms. If you go below 4 angstroms, you start to get a repulsion. If you go outside of 10 angstroms, then there really becomes no attraction at all. Okay. Now, one thing I want to mention about van der Waals is that van der Waals forces are actually pretty cool. Van der Waals forces, as I said, occur between any molecule, and van der Waals forces are what is responsible not only for helping DNA stay together, but for geckos and spiders attaching to the walls. So that's how they stick to walls. It's different than flies and other insects. Okay, that's a different way that they utilize that. But geckos and spiders specifically, the way they attach to walls is through van der Waals forces. I think that's pretty cool. All right, so let's move on to the properties of water. Now, first thing you need to know about water is that it's a polar molecule. Which means we have oxygen, which is highly electronegative, bound to hydrogens, which are not very electronegative. So therefore, we have a partial negative charge at the oxygen because it's trying to steal the electrons, and we have partial positive charges with the hydrogens, right? And this symbol that I'm writing here is a delta. Okay, so that's a delta, the Greek letter delta. Water is important because it is the solvent in which everything in the cell is dissolved. So we have to take into account water in anything in our living system. Now, water can hydrogen bond, okay? And you can hydrogen bond several water molecules together. A single water molecule can actually make 1, 2, 3, 4 different hydrogen bonds, okay, with 4 different oxygen molecule, or sorry, with 4 different water molecules. So the oxygen of a water molecule can hydrogen bond with 2 different hydrogens from different water molecules. And then each hydrogen of that original water molecule can hydrogen bond with an oxygen of a different water molecule. Okay? And if you look here on your right, this is the cubic form, so it's the crystal structure of solid water, which we know as ice. Now, water also is going to undergo hydrophobic interactions, and literally what hydrophobic means is hydro, water, phobic, afraid. Okay? So you can be hydrophobic, afraid of water, hydrophilic, water loving, philic, love. Okay, and we're going to talk about those terms, especially when we talk about proteins later in this class. So, hydrophobicity, so the not wanting to interact with water. So the hydrophobicity of nonpolar molecules promotes aggregation, so the coming together, by releasing water molecules in contact with their surfaces, enabling released water to form more hydrogen bonds with other water molecules. So imagine that this oil is in an aqueous solution of water, right? So it's surrounded by water molecules, right? Well, the water wants to interact with other water molecules more than it wants to interact with oil. And the oil desperately wants to interact with other things than water. So the oil wants to reduce its total surface area touching water. So what it will do is it will come together, okay, so it'll come together to push water out, right? It pushes all this water out, that surface area that's touching the water. So it'll basically erase all that, right? By becoming this big blob. And of course, water is still attached on the outside, but it's pushed out a lot of water in the process. So better for the oil. Now it is just touching less water, right? And better for the water because the water is touching more water than the oil itself. So this is a huge property of water, and this is important, okay? And we always think about our nonpolar molecules because of this. All right, so let's switch gears just a little bit to chemical reactions and free energy. So in a reaction, A plus B going to C plus D, there's always something called an intermediate or a transition state that we usually do not see. Okay, and that is the point that we call here AB. That is the point at which it is transitioning from the reactants A and B to the products C and D. And this usually occurs via an enzyme. Okay. Now, the rate of a reaction is affected by the concentration of the reactants as well as the concentration of the products. The rate will also be affected by the energy barrier, the temperature, as well as the pH of the solution in which the reaction is occurring. Now, when we're talking about chemical reactions, it is extremely important to know that forward and reverse reactions are occurring simultaneously. So it's happening in both directions. Okay? But the speed of reaction in, say, the rightward direction versus the leftward direction differ. And that is what allows you to either make a bunch of products or stay with a bunch of reactants. Okay? Now, this equilibrium state is a very dynamic state where the rates of your forward and reverse reactions are equal. Now, it's important to note that forward and reverse reactions are still occurring, but there is no net change of reactant or product, okay? Because if one reactant is being turned into a product, then one product is being turned back into a reactant, okay? So forward and reverse reaction still occurring, but at the same rate. So at a zoomed out macro view, nothing is changing, okay? And you can measure the equilibrium because each reaction is going to have an equilibrium constant, which is KEQ, K sub EQ. And that is going to measure the extent to which reactants are converted into products. It's a very simple measurement. I mean, you can get much more complex, but I'm presenting a simplified one. Is that the KEQ is equal to the concentration of your products over the concentration of your reactants. And so from here, you can understand that if you have your numerator, right, bigger, right, so KEQ is going to be greater than 1, then the reaction favors the products. If you have the denominator larger, you're going to have a number less than 1, and that reaction is going to favor the reactants, so the backwards, right? So, as an example of these, I want to show a very cool aspect of chemical reactions. So, in the following reaction equation, label the reactants and the products. Okay? So, as we talked about before, I'll work this through with you. A plus B going to C plus D, right? You're starting with this, so these are going to be your reactants. And you're ending with C and D, so that's going to be your products. But this is a double-headed arrow that we see right here. Okay, it's a double-headed arrow, meaning this reaction is reversible. It can go in both directions. So, in the other direction, C and D are your reactants, and A and B are your products. So all four A, B, C, and D are reactants, and all four A, B, C, and D are products at one point or another in this reaction. Okay, so rightward reaction, A and B reactants. Leftward reaction, C and D reactants. So continuing on with our chemical reactions and free energy, I want to introduce the concept of activation energy, also shown as E sub A. Now, activation energy is the minimum energy that is needed to be input to cause a chemical reaction. Okay? So when two reactants, let's say X plus Y, collide, energy gets released. It has to be greater than the energy barrier for the reaction to proceed. And this energy barrier is that amount of energy required for the formation of the products. So this is your energy barrier or your activation energy. Okay? Because this is the energy of your reactants, and this is the energy of your products. And even though your energy of your products are lower than your reactants, you have to pass this hump, this threshold, to be able to get down to here. So let's talk about enzymes, right? Enzymes are biological catalysts. They accelerate reactions by decreasing the activation energy. Okay? Now, enzymes do not affect the reaction equilibrium, okay, the KEQ, or the change in the free energy. But they can decrease this, right? Let's say with an enzyme, my curve might look like this. Okay, so this is my activation energy with an enzyme. Right, but they should end in the same place. This is my activation energy without an enzyme, which is much higher. Okay, good. But, as we can see, the energy of the reactants and the energy of the products is unchanged. So let's give a few statements about chemical reactions and free energy. So what is free energy? We usually talk about it as Gibbs free energy and as the change in Gibbs free energy. So delta G. This is the difference between the free energy of the products minus the free energy of the reactants. Now, as we saw back there on the previous slide, we had two different looking graphs. Okay, this is reaction progress. Okay, and this was free energy. Okay, and we know that the left tail, this is our reactant. The right tail is our product. And we know that this is our activation energy, right? Our energy barrier. Now, if your products have a higher free energy than your reactants, what do we have? The difference between the free energy of the products, so what we're looking at is the G of our products minus the G of our reactants. Okay, that's our delta G. So, if our products have a higher, if they have a higher energy state than our reactants, that delta G is going to have a positive sign. Okay, meaning you need to add in energy from the system, usually in the form of heat or ATP, to get up to this energy level. Okay, that usually means that the reaction is non-spontaneous. Okay, it won't happen on its own. You need the input of energy. Okay, and this is also called an endergonic reaction. Okay, now let's look at the flip side. If our energy for our products is lower than our energy for our reactants, we're going to have a negative delta G. That means that it's actually going to give energy off to the system in the form of heat or ATP energy. Okay? This will likely be spontaneous, meaning it can happen because you don't need to input any energy. This is called an exergonic reaction, and it's likely to happen. Now, when your reactants and your products have the exact same amount of free energy, that's when you're saying that the reaction is at equilibrium. Okay, so you're no longer going one way or the other. Okay, and what's important here is that delta G ultimately determines the final concentrations of reactants and products. But not the reaction rate. Okay, Okay, the reaction rate is determined by the enzymes, right? By the activation energy. Okay. Good. All right, so over here, remember if we have the reactants, products, we have our activation energy. Okay. This is endergonic. You need to put in energy because the products have a higher energy than the reactants, meaning this is delta G of positive, right? Meaning endergonic, positive delta G, non-spontaneous. In this reaction, the reactants have a higher energy than the products, meaning they're giving energy off to the system, meaning it's exergonic. The delta G is negative, and it is likely to occur, right? Spontaneous. So, one thing about spontaneous and non-spontaneous, are negative delta G, positive delta G, is that just because you have a positive delta G and it's a non-spontaneous reaction doesn't mean it will never occur. Reaction coupling is what happens when you can add a negative delta G to a positive delta G reaction to allow that positive delta G reaction to occur. So what happens is that the second reaction consumes the products of the first reaction, preventing reverse of the reaction, which would otherwise be favored. So if you can, let's say, have, in the big scheme of things, here's our progress. Here's the free energy. Right, and that's going to go that way. What you could actually have here right? This could be a reactant. Product. This could be reaction 1. And as we can see here, the products are much lower in, I don't like how I do that. They are much lower in energy than the reactants. Therefore, it is highly negative delta G. This can be coupled to another reaction where it is a positive delta G, right? And actually, this product of reaction 1 now becomes the reactant of reaction 2. Okay? So that is how they can be coupled to force a positive delta G non-spontaneous reaction to go forth. So let's quiz you based on the last couple slides. What information can be gleaned from a reaction with a negative delta G? All right, we ready? So, a negative delta G reaction is going to tell you that a reaction is spontaneous, that no energy input is needed, and in fact, it gives off energy to the system. It will favor the formation of the products. Negative delta G affects the equilibrium, but not the rate, and it may be coupled with a positive delta G reaction to force that to proceed. All right, so that's all the biochemistry review that I wanted to do, but I also wanted to introduce you to DNA. We're going to go into DNA in much further detail in a few lectures, but I wanted to introduce it to you first, all right? So DNA stands for deoxyribonucleic acid. That's what the DNA stands for. So I'll write that out for you. Deoxyribonucleic acid. Okay, the A, the D, the N. Okay. Now, DNA is normally found in what's called a double helix. So it's two-stranded, as we can see over here. Okay. And it is in an anti-parallel orientation. Each strand has a 5' phosphate end and a 3' hydroxyl end. Okay. And when it is in a double helical form, you have one strand, if we're just going to read this from top to bottom, going 5' to 3'. And it is bound to its complementary strand in the opposite or anti-parallel orientation, with 5' going up to the top of the page to the 3' hydroxyl end. Okay. Purine bases and pyrimidine bases are two types of heterocyclic nitrogen bases that are parts of a nucleotide. And a nucleotide is the monomer of a nucleic acid. Purines are two-ringed heterocyclic nitrogen structures. Pyrimidines are a single-ring structure. And purines and pyrimidines always pair together. So adenine is an example of a purine, and it will hydrogen bond to thymine, which is an example of a pyrimidine. Okay? Guanine is an example of a purine. Okay, down here. And cytosine is an example of a pyrimidine. They will hydrogen bond. Okay? G's and C's always make 3 hydrogen bonds, as you can see here. A's and T's always make 2 hydrogen bonds. Under normal circumstances, A's only bind with T's in DNA, and G's only bind with C's in DNA. Okay? And on the outside, so those bonds are on the inside, on the outside is the phosphate backbone that links the nucleotides of the same chain together. Okay? So I said before, we have the bases on the inside making hydrogen bonds. Okay, 2 between A's and T's, 3 between G's and C's. This right here is an example of a nucleotide. These are the monomers of DNA, right, of the nucleic acid polymer. It has to have a nitrogenous base, so a purine in this case. A pyrimidine could also work. A sugar, if it's DNA, it is deoxyribose. If it, so it's just an H here. If it were to be RNA, it would be an oxygen there, right? So that hydroxyl would be there. And it must have a phosphate group. All right. Now, just a few other quick things on DNA. It has several forms, A, B, and Z forms. The normal is B form that's found. And there is 10.4 base pairs per turn of the helix in B DNA. So say from here to here is one turn. Okay. So there's 10.4 base pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. There are both major and minor grooves on the surface of the helix. So we have the major groove, okay, and it goes this way. We have the major groove and then the minor groove, okay? And these are important because, as we'll talk later, you can see more of the chemicals, okay, the atoms in the DNA, so that helps for DNA binding of proteins, right? What's important, and I've talked about earlier in this unit, is that hydrogen bonding and hydrophobic interactions, also known as base stacking interactions, hold the two strands together. And our DNA can be denatured and renatured, meaning you can break and remake the hydrogen bonds, kind of as if nothing ever happened. Okay, you're not breaking the molecule at all, you're just separating the two chains. Think of it like an ice cream sandwich, right? The two cookie crusts are your DNA strands, and your ice cream is your hydrogen bonds. If you want to denature your double-stranded DNA, you just melt those hydrogen bonds, okay? A couple ways to do it is actually with heat. So, right, if you microwave your ice cream sandwich, which would just be a waste of an ice cream sandwich, but if you did, you'd be able to pull apart those cookie crusts really easily. Okay, another way to denature double-stranded DNA is if you put it in a high pH environment or low salt concentration, or if you add metabolic enzymes that are made to break that open. A cool thing about DNA is that the same complementary DNA strands that were denatured can renature or reanneal when the environment is brought back to normal. So if you decrease the temperature, if you decrease the pH, if you increase the salt, okay, certain things like that. And DNA strands will anneal to what it should have annealed to, what are called complementary sequences. So A's and T's will come back, G's and C's will come back to each other. And speaking of the ability to denature and renature, I want to introduce you to a concept called hyperchromicity. And what hyperchromicity is it is just the increase of absorbance of a substance. Now, single-stranded DNA absorbs more UV ultraviolet light than an equal amount of double-stranded DNA, and almost about 20% more for the same. So if single-stranded DNA, if you had 10 base pairs, right? Or sorry, it would be 10 bases because it's single-stranded, and you had 10 base pairs of DNA, this 10 bases of RNA would absorb about 20% more UV light than double-stranded DNA. And that's because the actual nitrogenous bases, right, the A's, T's, G's, and C's, the purines and pyrimidines, are what is absorbing that UV light. But when it's in a double-stranded helix, they're compact inside on the inner portion of the double helix. Single-stranded DNA or single-stranded RNA, those flap out in solution, okay? So what we can do, we can determine at a certain point based on the absorbance, okay? If we have microscopic DNA, we can't see it in solution, but we'll be able to tell if it's DNA or RNA, or if it's double-stranded specifically or single-stranded. And how we do that is we use a machine called a spectrophotometer. And we make a reading, we take a sample of DNA in water or a buffer, put it into a clear tube that we call a cuvette, put it in a machine. You shine light through one side of the cuvette, and you have a detector on the other side, and it will calculate how much of the original light came all the way through, how much was captured. All right, and they do that at a wavelength of 260 nanometers. Well, at this low wavelength, at this wavelength, okay, we're reading absorbance values. So an absorbance of 0 means that it's completely translucent. All the light went all the way through. At an absorbance of 100%, that means it's completely blacked out. Not a single photon of light went from the light to the capturing device, okay? So at this absorbance level, we have everything being double-stranded. As you increase the temperature, you start to denature the DNA. So you start to melt those bonds. As you melt the bonds, the nitrogenous bases start being able to flap around in solution more, meaning it catches more UV light, so it absorbs more. Okay, and to the point where you're completely denatured, so this is double-stranded DNA, until you're completely denatured, and this is actually single-stranded DNA, where it has the full absorbance. Right here at the inflection point is what we call the TM, or the melting point. The melting point is the point at which you have 50% of your DNA as double-stranded and 50% as single-stranded. Okay? And the TM, the melting temperature, is determined by the base sequence as well as the salt concentration. Okay? That can affect the shielding, and we're not going to get into it, but salt concentration will affect if you denature or not. Okay. So for our last portion of this unit, I want to leave you with a very crude method to approximate our melting temperature without using any type of absorbance values, molecular techniques. So for example, the crude method is that for every AT base pair, that equals 2 degrees Celsius. And for every GC base pair, that is 4 degrees Celsius. We usually calculate this when we are making primers for polymerase chain reaction, PCR, which is another thing we'll learn in this class. But I wanted to give you a sample problem. So, for example, let's say we have this sequence, AT, G, C, AT, G, C, A. So what would the melting temperature of this 10 base pair sequence be? Okay, so we have count up how many A's and T's. AT bonds are 1, 2, 3, 4, 5, 6. Okay, so that leaves us with how many GCs? 1, 2, 3, 4. Okay, 6 AT bonds times 2 degrees Celsius equals 12 degrees Celsius. 4 GC bonds times 4 degrees Celsius equals 16 degrees Celsius. Add those together, that gives us a melting temperature of this sequence of 28 degrees Celsius. Okay, and as you'll be able to see is that regions with higher GC content will have higher melting temperatures, and regions with higher AT content will have lower melting temperatures comparatively. Well, thank you for joining me at educator.com, and I hope you come back and see me in lecture 2. Thank you.